Hi everyone, welcome back to another GCSE Physics webinar. Today's webinar is going to be carrying on our nuclear physics topic and finishing it off so we can go through lots of exam questions today. What we're going to be looking at as our final part is nuclear fusion. As always, these sessions are 1 hour long, and it will be recorded and uploaded to YouTube so that you can refresh, revise and get down any notes that you didn't before. If you don't know me already, my name's Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. So what we're going to cover today is what happens in a fusion reaction, understand fusion processes that happen in the sun, understand why fusion reactors are not really a viable option, understand what background radiation consists of, which we briefly touched on yesterday, understand why nuclear waste is an issue, nuclear disasters, and why half-lives can be an issue. So split into two kind of sections today for our content: nuclear fusion and nuclear issues. So looking at the issues that kind of mean that nuclear power cannot be utilised as effectively as we would want. We'll go through some example questions as always, and there'll be time for your guys' questions at the end. If you have any questions throughout the session, please don't hesitate to put them on the chat or the Q&A. You can submit them anonymously if you'd like, and I will try to get to them as soon as possible, or I will answer them at the end. Okay, so let's start off with a brief summary of what we did yesterday. And that is looking at radioactive tracers. So we're looking at nuclear medicine, and we started off by looking at how it can be used for radioactive tracers. So using a gamma emitting source, such as iodine in the kidneys, and tracking how the iodine flows through the kidneys because it releases gamma, which can be detected outside. Then we looked at gamma cameras, which is this application of gamma radiation, which allows us to take pictures of internal organs. Then we looked at gamma radiation for cancerous cells. So that's shooting a beam of gamma rays at a cancerous cell and hopefully destroying that cell. Radioactive implants was the 4th application that we looked at, which is actually injecting the source and the organ absorbs it. This can be a beta or a gamma source, and again, we want to destroy that cancerous cell or even a tumour. We looked at the kind of toss-up between having a half-life that is short enough to suit its medical purpose, so either to take an image or to be able to be tracked, and long enough so that you can take an image and use it for the medical purpose, but short enough so that it will decay and won't stay in the patient's body for a long time. So then we looked at how we can reduce our risk, which is by using personal protective equipment, wearing radiation monitors, and just keeping our exposure time low and our dosage low. However, if we're just kind of normal day-to-day life and we're not around any nuclear power plants, there is background radiation, but it's a very, very low risk. Then we went on to nuclear fission, looking at fission reactors, fission neutrons, chain reactions, fissionable isotopes, and finally the nuclear reactor. And that was all about fission, which is taking a nuclei and splitting it into 2 smaller nuclei, and then releasing some neutrons in the process, and those neutrons going on to create more and more fission events, and eventually getting a chain reaction, which all happens in a nuclear reactor, which we looked at the features of. Now, before we start the content for today, I do want to give you guys what you want. You all seem to want the quizzes, so we're going to do another quiz at the beginning. It's the same quiz as yesterday because one of you put a really good idea in the chat, which was to do the same quiz again and see if we can improve our accuracy. So it's the same quiz as yesterday. So yeah, I'll put it on the screen now. If you've not done one of these quizzes before, what you need to do is either go onto your smartphone or open a new tab on the computer or laptop that you're watching this on. and you want to type in the website joinmyquiz.com, which you should see on your screen now, joinmyquiz.com, either on your smartphone or your laptop, and type in this game code 251323, and I will put the link for the quiz on our Zoom chat so that you can all see it there, and you can join through the Zoom chat if you like. So either type in the game code or access through this link. Someone's just asked what year do we usually learn this? This would tend to be a year 11 topic, just because it is one of the more advanced topics. But yeah, there's not really kind of any set topic that you do in a set year. It's really up to the teachers, but yeah, it is one of the more advanced topics. So I would say probably year 11, end of year 11. Okay, got 16 of you on, and there's 26 of us today. So we'll wait for a few more. Okay, 18, 19 of us on, 20, and there's 2 of me. Okay, we'll start now. If you guys do want to join, you can join halfway through. The link is on the Zoom chat, so just join through there. We're going to start. You guys will have roughly 20 seconds per question. They are multiple choice, and do your best just to answer. We'll be going through the answers at the end if you guys do get any wrong, so don't worry. Well done, guys. We've already got a better accuracy than yesterday. We're on 72. Let's try and keep it there. Yesterday we got 66, so let's make sure that we beat that accuracy. 72% accuracy. Let's try and keep it up. Really good, guys. Some of you are getting 100%, which is really, really good. Okay, about half of you are done. I'll give us 2 more minutes to finish that off. Okay, let's start going through the answers while the rest of you just finish off. So, what is a beta particle made up of? A beta particle is simply an electron. Of the main types of radiation emitted from naturally radioactive isotopes, which is the hardest to block? The hardest to block is gamma. Gamma can get through a lot of things and it's only stopped by lead or concrete. What is emitted during beta radiation? Same as the first question, really. It's just a high energy electron. True or false, gamma changes the atomic number. The atomic number is the number of protons. And because gamma is simply a wave, it doesn't have protons, neutrons, or electrons. Gamma is just an electromagnetic wave. So it does not change the atomic number and it does not change the mass number. What is emitted during alpha radiation? This is a helium nuclei. Loads of you got that correct, so really well done. Not a helium atom. Remember, we don't want to bring the electrons with us. What is radioactive decay? This one's slightly harder because they are all quite similar definitions, but it is a spontaneous breakdown of an atomic nucleus resulting in only energy release. Which type of nuclear radiation is being emitted here? You pretty much all got that correct, so really well done. And you can see here that it's an electron that we're getting emitted and therefore it's a beta particle. or beta radiation. When does radioactive decay occur? Radioactive decay occurs when our nucleus is unstable. Again, loads of you getting that correct. Really well done. When it's unstable and it releases radioactive decay to try and get more stable. Isotopes of the same element have different number of neutrons. The definition of an isotope is the same number of protons, different number of neutrons. Complete the nuclear equation and determine the type of decay that is occurring. The type of decay that is occurring is alpha, because the mass number changes by 4 and the atomic number, the bottom number, goes from 88 to 86. So we know that it's 4-2, which is helium nucleus or alpha radiation. How many protons does the gold atom have? Only one of you got this wrong, so really well done. The answer is 79. Although 197 is the bottom number, the number of protons is always going to be the smaller number, except for the case of hydrogen, where they're equal. What is the mass of an alpha particle? Mass of an alpha particle is 4. Definition of an isotope is a different number of neutrons. Neutrons have no net electric charge. The number of neutrons in cesium is 139 minus 55, which is 84. And the atomic number of a given element is equivalent to the proton number. So atomic number just means the number of protons, and the mass number means protons plus neutrons. So really well done, guys. We improved on our accuracy by 8%, so that's really, really good. Okay, so let's move on to the main content for today, because we've got quite a lot to get through. So yesterday we looked at the nuclear reactor, and that was talking about nuclear fission. Now today we're going to be talking about nuclear fusion, which is this idea of fusing two smaller particles together and creating a bigger particle, which you can see in this diagram here. Now stars do this very process. The way that stars work is through nuclear fusion. They're constantly fusing hydrogen together to create helium. And those two smaller nuclei, when they fuse, release some amount of energy. Okay, they release some amount of energy when they fuse. Now, one really interesting fact about nuclear fusion is that when the nuclei fuse together, some of the mass of those nuclei gets converted into energy. So let's say the mass of this nuclei is, 1. The mass of this nuclei is 1. Okay, just random numbers, don't really mean anything, just 1. Now, some of that nuclei mass, let's say 0.2, gets converted into energy. So the mass of this product that we create is actually going to be smaller than the mass of this plus this. The mass of the nuclei that we create will be smaller than the mass of the nuclei that created it, because some of the mass of that nuclei is getting changed into energy. Now we can take it one step further, and it's slightly out of your GCSE syllabus, but I think it's quite interesting. Everyone knows the really famous equation by Einstein, E = mc². Now, all that equation tells us is that we can change mass into energy, or energy into mass. And that's exactly what's happening in nuclear fusion. Some of the mass of that nuclei is being converted into energy. So don't worry about that equation. I just thought that it might be a little bit interesting to have you guys see that energy can be changed into mass and vice versa. Now, another important fact about nuclear fusion is that it only happens if the mass number is no more than 55. Okay, so our top number in our periodic table is no more than 55. And there's a whole explanation for that, which you don't need to go into for your GCSE, but actually 55 is the mass number of iron. Okay, so if the element is heavier than iron, then it needs some sort of extra energy to fuse. If it's lighter than iron, it's fine, they can fuse and they can create a heavier nuclei. So it needs to be lighter than iron. Otherwise, if it's heavier than iron, it needs more energy to fuse. Okay, so fusion reactions in the sun then. We know that sun and stars constantly fuse hydrogen to protons together, and they form a heavy hydrogen nucleus to one hydrogen. So hydrogen looks like this. And when it fuses with another hydrogen, we get so what we see here is two protons fusing together to create a heavy hydrogen nucleus. At the same time, other particles are created and emitted. Two more protons then collide separately with two heavy hydrogen nuclei and turn them into even heavier nuclei. Those two heavier nuclei then collide to form the helium nucleus. Now, this process is, again, not really in your specification. It's never tested, and it's just a really small kind of fact kind of process that they include for extra information. It's never tested, so it's not really something that you need to remember. It's just an example of how fusion happens in stars. And fusion reactors, then, we've said, are not really viable machines, not really viable reactors. And the reason for this is that light nuclei have to be at a high temperature and a high pressure to fuse. Okay, light nuclei need to be at a high temperature and a high pressure to fuse. Now, to be able to create a high temperature and a higher pressure is a lot of effort. We have to get it really, really hot and really, really dense to mimic the conditions in a star. So that's a lot of effort. It's a lot of cost, it's a lot of energy, and it's really hard to do on Earth. And that's why fusion reactors are just not viable. It's not cost effective for us to make fusion reactors. Now, the reason that we need this high pressure and this high temperature is because naturally two nuclei want to repel each other. Naturally, they want to repel each other. But if we get them moving fast enough, then they can overcome this repulsion and fuse. But only if we get them moving fast enough. And the only way that we can get them to move fast enough is through either having a high temperature or a high pressure. So to be able to create this fusion, we need to have this high temperature or this high pressure. Now, a fusion reactor, although it's not really a viable option to create, would actually be a really great way to solve our energy problems, because the fuel needed for them is naturally found in seawater. The product of fusion is not harmful. It's just helium. It's not harmful to anything. And it would allow us to generate electricity. So the fuel is naturally occurring. It's in our seawater, which we have an abundance of. The product of the reaction is not harmful. So there's no nuclear waste, and we can generate electricity. So that would all be really, really good kind of effects. However, we're not really good at creating them. Now, fission reactors use uranium. As we saw yesterday, fission reactors use uranium. Now, the reason that this is a problem is because uranium is only found in certain parts of the world and it has to be mined, as well as the fact that fission reactors create nuclear waste, which must be stored for a long, long time. Okay, so let's move on to nuclear issues. As you can see, nuclear fusion is actually not that big of a topic. All you really need to know about it is that elements heavier than iron can't fuse without some input energy. Elements lighter than iron can fuse kind of on their own. When elements fuse together, they create some energy, they give off some energy, and not all of the mass gets converted into all of the mass. Some of the mass gets converted into energy. Then you can talk about the differences between the fusion and the fission reactor, and the fact that the fusion reactor is not really a viable option. So fusion is a much kind of smaller topic and less tested topic than fission is. So let's move on to background radiation. Now, we've touched briefly on background radiation yesterday, but let's go into a bit more detail. We know that background radiation exists because a Geiger counter, remember, a Geiger counter is the apparatus, the piece of equipment that we use to measure radiation. So when we have a Geiger counter just sat there, no radioactive sources near it, no radiation near it, it is clicking. It is picking up some radiation, and no one's put any source near it, so there must be some radiation in the air. And this can cause problems for scientists if they don't account for it properly, because it might give radiation readings higher than what we expect them to be because of the background radiation. So we know background radiation exists because the Geiger counter clicks when there's no source near it. But where does this background radiation come from? Well, it comes from a number of different places. The most radioactive, the highest percentage of the radiation in background radiation comes from natural radioactivity in the air. We can see that it's got the highest radiation dose, 1,190. So most of the radiation in our air comes from radon. And radon is a gas in our air which can be harmful if breathed in for long periods of time, and a lot of it. So radon can be harmful, but the dose that we're receiving in day-to-day life will not harm us. However, sometimes if there are radioactive rocks underground, the radioactivity can seep in to the air and cause problems. It can seep into buildings and cause problems because those people in those buildings are constantly breathing it in, and therefore pipes underground are installed to suck the radon gas back out. The reason that radon can be harmful is because it emits alpha radiation. Now, if it emits alpha radiation, we obviously know that that can be harmful if it's close to us and not being blocked by anything. Other places that background radiation can come from are the ground and buildings, and medical applications such as X-rays. Food and drink, cosmic rays, so that's cosmic rays coming from space, nuclear weapons tests, air travel, and nuclear power. So you can see that the lowest radiation dose comes from nuclear power. And nuclear power, when you talk about it, it seems quite scary because it can be dangerous and it can be harmful. But actually, the lowest radiation is coming from those nuclear power plants. Okay, nuclear waste. Nuclear waste is a product of nuclear fission, as we saw yesterday. So fission, remember, happens in a nuclear reactor, and when fission happens, we get nuclear waste from the fuel rods. So we'll go all the way back to fuel rods, which you can see here, and these are made up of uranium. That's where all the radioactivity is stored, in those fuel rods. That's what's creating the fission. And so those fuel rods, after the nuclear reactor has kind of been worn down, it can't really be used anymore, need to go somewhere. But they're really hot and they're really, really, really radioactive. That makes them a big, big problem to dispose of. So once our nuclear reactor is worn down and it's not really useful to us anymore, we need to get rid of these fuel rods. So what we do is we store them in tanks of water for years and years. And that water allows it to cool down and take some of the radioactivity away from it. The machines are then used to open them. So we have some special machines which open these fuel rods, and the uranium and the plutonium that is inside of them is scraped out and reused. So that is one kind of good use of fuel rods. They are reusing the radiation that is in them. And then the material that is left over are the isotopes, has a long half-life. And a long half-life is a problem because it takes a long time to decay. And therefore we must store it securely and out of the way of harm of humans, which means it must be stored underground. But if we keep doing this, eventually we're going to run out of storage areas for it. Okay, so another nuclear issue that you may have heard of is the Chernobyl disaster that happened in 1986. So in 1986 in Chernobyl, a nuclear reactor exploded, 30 people died and hundreds of thousands of people had to be evacuated. The cancer cases went up and lots of people got leukemia. This happened because Chernobyl ignored safety advice. And so what we learned from that nuclear accident is lots and lots of different ways that we can improve our safety, and out of it came kind of greater risk assessment. Okay, and then another nuclear issue that we have is half-lives and instability. So isotopes with the shortest half-lives have the most unstable nuclei and lose a lot of radiation quickly. Half-lives can have a huge range of quantities. It can be a fraction of a second to thousands and thousands of years. And if an isotope has a really short half-life, then it's really, really unstable and it will lose a lot of radiation quickly. The half-life tells you how quickly its activity decreases. We know this, the half-life tells you how quickly activity decreases. But as its activity decreases, the rate at which it gives out radiation also decreases. So as activity goes down, how quickly it gives out radiation also gives down. So that means that isotopes with really short half-lives are really radioactive in those first kind of seconds, which can be bad if we don't use the correct safety advice. Okay, that is all of our content. I'm going to go through some questions now, but if you guys do have any questions still remaining, please put them on the chat, please put them on the Q&A. Okay, someone said energy can't be created or destroyed, so how can we go from mass to energy? Well, it's not being created or destroyed, it's simply being transferred from the form of the mass into the form of energy. It's not being created, it's just being transferred from the mass to the energy. Why is it called half-life? Okay, it's called half-life because it's the time taken for the number of nuclei to half, or the activity to half. Someone said, what about electrons? And I'm really sorry, I don't know what you're referring to. So if the person who said, what about electrons, could please clarify what that's referring to, that'd be really good. Is there any others? Okay, someone said, but cesium is 55. Okay, so someone said cesium is 55, so why is iron 55? Now, iron is this is an isotope of iron. Iron 55 is an isotope of iron. Not the iron that you see on the periodic table. So let's have a look. Iron periodic table. Okay, so what we see on our periodic table is that iron is actually 56 when you round it up, right? It's 56 as its mass number. Now, what that means for us is that actually, if we have iron 55, that's an isotope. It has a different mass number, but we still have the same number of protons. So iron 55 is the isotope of the boundary, okay? Iron 55 is that boundary between either needing more energy to make it fuse together or not. Okay, it's that boundary, it's that cutoff point between elements that are light enough and elements which are too heavy. So when I say iron 55, I mean an isotope of iron. Okay, doesn't look like there's many other questions. So we'll move on to some example questions now. Okay. Hopefully you guys can see this okay. So this is an exam question taken from the AQA exam board about the average dose of background radiation that the average person receives in Britain. So you can see the source of background radiation and the average amount each year in dosage units. So 50 from buildings, 1,250 from radon, similar to the table that we just saw. Now, only two of the following statements are true. Half the average background radiation dose comes from radon gas. Everyone receives the same background radiation dose, or cosmic rays produce less background radiation than food and drink. Which ones would be true, do we think? Put your answers in the chat. A, B, or C, which two are true? Okay, lots of you saying the correct answer. A and C, that's good. So for the first one, A, we see that half of the total comes from radon. Total is 2,500, half of that is 1,250, so that is true. Cosmic rays produce less background radiation than food and drink, so cosmic rays produce 240, food and drink produce 300, so we can see clearly that cosmic rays produce less background radiation than food and drink. And finally, everyone receives the same background radiation dose. Not true, okay? This is just average person in the average location, going for an average amount of X-rays, being exposed to an average amount of radiation. However, let's say you have more X-rays that year than somebody else. You're going to receive more background radiation dose. Still won't be harmful. You can have literally thousands of X-rays and you still won't be harmed. But that does mean that lots of people will have different exposure to radiation. Then you have people that have got cancer, people who go for X-rays very often, people who live near nuclear power plants, and so on and so forth. Okay, most sources of background radiation are natural, but some are artificial or man-made. Which source of background radiation from the table is artificial, do we think? Which source is artificial and which sources are natural? What do we think? Okay, so which ones would be artificial is actually medical treatment or x-rays. Everyone else is naturally occurring. So food and drink is just natural elements, natural potassium, calcium, iodine, whatever it happens to be, are naturally radioactive sources. Buildings, again, natural because it's created from radioactive elements, which are naturally occurring. Radon, again, naturally occurring gas. Rocks, naturally occurring. Space and cosmic rays are naturally occurring. Medical treatments, we have to create those X-rays. Okay, so not always naturally occurring. Each time a dental X-ray is taken, the patient receives about 20 units of radiation. So, sorry, that might be a bit small. Each time an X-ray is done, 20 units are received by the patient. Okay, how many dental X-rays would give the yearly average dose for medical treatments? How many dental X-rays would give the yearly average dose for medical treatments? So we see that the average dose for medical treatments is 300, and they want to know how many X-rays would give the yearly average dose. If each X-ray is 20 and the total dose is 300, how many X-rays on average are done per patient? Okay, so it should just be a simple division, just doing 300, which is the total, divided by 20, which is the amount per X-ray. So when we do 300 divided by 20, we should be getting 15. So you should be getting 15 as the number of X-rays, and well done if you got that. Okay, radiation is around us all of the time. This pie chart shows some of the sources of that radiation. What is the main source of this radiation? So we can clearly see from the pie chart that the main source, the biggest percentage, is radon. What name is given to the radiation that is around us all of the time? That is called background radiation. Name that is given to the radiation that is around us all of the time is background. Now, one thing to note about background radiation is that they might ask you an exam question about why background radiation might be a bad thing for scientists. And the reason for this is because scientists get higher readings than they expect because of this background radiation, and therefore we need to account for it. It's not damaging, it doesn't ruin our experiments, but we do have to make sure that we take it into account. Okay. How are stars able to give out energy for millions of years? Do they join atoms together? Do they split atoms apart, or do they burn gas? What do we think? Which one? A, B, or C? Atoms joining together, atoms splitting apart, or by burning gases? What do we think? So for Stars actually work by fusion. Okay, so stars work by joining atoms together. They're constantly fusing hydrogen nuclei into helium nuclei. I've already done this question quite a lot, so we'll skip this one. If you guys do want to have a go at it later on, then just go onto the YouTube video and have a go. Okay, to study the blood flow in a patient's lungs, a doctor injects some I don't know how to say that word. Technetium, okay, whatever. Technetium 99 compound into the patient. The gamma radiation given out by the I'm just going to call it T99 atoms is detected using a gamma camera outside the patient's body. So this question is all about using a gamma camera after having injected some radioactive source. Which statement gives the reason why gamma radiation is used? So why don't we use alpha or beta in gamma cameras? What's the reason? It can travel through a vacuum, it is not affected by a magnet, or it can pass through the human body. This one might be a bit kind of obvious. The answer is it can pass through the human body. It doesn't really matter that it can travel through a vacuum because our bodies aren't a vacuum, and it doesn't really matter if it's affected by a magnet because there shouldn't be a magnetic source there. Okay, this one is about fission. So we have our reactor, and don't worry about this part here. So which substance do the majority of nuclear reactors use as fuel? Is it plutonium, thorium, or uranium? What do we think? What is the main source of fuel for nuclear reactors? Okay, so this would be uranium 235 or 235. That is the main one that we use for fuel in nuclear reactors. Then for part B, the nuclei splits down into smaller parts and releases some neutrons named fission neutrons. So I'll just write that down for you guys. Nucleus splits into two smaller parts and some neutrons are released. You might want to say fission neutrons, up to you. Mark scheme doesn't specify. Okay, which two of the sources listed in the box are natural sources of background radiation? So which two are natural sources? What do we think? What are naturally occurring sources? They have no human input whatsoever. Feel free to abbreviate your answers if you want. You don't need to write out the whole words. I'm sure I know what you mean. Okay, those of you getting the right answer for this one, the natural sources would be cosmic rays and radon gas. They're naturally occurring. They need no human input to occur. X-rays and nuclear accidents happen because of humans. Okay, so this one is quite a good question because it will help us to consolidate all the key terminology which we've learned. So on the left, you have the definition, and on the right, you have the key term. So first of all, we have gamma emission, then we have electric current, then we have ionization, nuclear fission, and nuclear fusion. You need to join all these four for the 5 on the right. You only need to draw 4 lines. As you can see, there are 5 in list B and 4 in list A. So I'll give you 1, 2, 3, 4, and A, B, C, D, E on the right. And then let me know which ones you think match up. So what do we mean by the nuclei of two atoms joining together? What do we mean by the nucleus of an atom splitting into several pieces? What do we mean by an atom losing an electron? And what do we mean by an electric charge moving through a metal? Okay, so let's have a look at what you guys have put. 1E, 2D, 3A or 3C, and 4B. Okay, so we all seem to agree that 1 is E, which is correct. The nuclei of two atoms joining together is nuclear fusion. Nucleus of an atom splitting into several pieces is nuclear fission. An atom losing an electron is ionization. So ionization is all about knocking an electron out of an atom and making it a charged particle, an ion. So ionization is the process of knocking an electron out of an atom and creating a charged particle known as an ion. Okay. And finally, an electric charge moving through a metal. Well, the flow of charge is current. So one that they've kind of thrown in there to throw you off a bit, but that one would be electric current. Nothing really to do with nuclear physics, taking knowledge from another area of your specification and applying it. It doesn't happen often, but yeah, no, it can happen, and you need to be aware of the fact that they can do that. A teacher used a Geiger Miller tube and counter to measure the background radiation in her laboratory. The teacher reset the counter to 0, waited 1 minute, and then took the count reading. The teacher repeated this 2 more times. So the teacher puts it to 0, waits for a minute and takes a reading, resets it to 0, waits a minute and takes a reading. So they're measuring background radiation. Background radiation can be measured when there's no radioactive source there. And these are the results that the teacher got: 17, 21, and 19. Now the readings are different. What is the most likely reason for this? Did the teacher not reset this counter to 0? Did she change the temperature in her laboratory? Or is it the fact that radioactive decay is a simple is simply a random process? What do we think? A, B, or C? We definitely know it's not A, because in the question it tells us the teacher did reset the counter to 0. So we'll cross that one up. What do we think? Did the temperature in the laboratory change, or is radioactive decay just simply a random process? And that's the reason why she might have got 3 different readings. Okay, few of you putting C, few of you putting B. Let's clear that up. So the temperature in the laboratory changing does not have any effect on radiation. Okay, so it's not temperature. Temperature is not related to radiation. Answer would be radioactive decay is a random process, and therefore we can't be getting the same reading every time because it's so random we can't predict. It's not always going to be 17. Okay, so I think we'll stop there today. Hopefully you guys have got a really good understanding of nuclear physics. Remember, you can go back to each of the webinars, take some notes, revise. They'll be there for a long time, so hopefully you'll be able to access them whenever you need to revise. Yeah, that marks the end of the nuclear physics topic, and do have a go at those exam practice questions again, and I'll put some more ones up just while I'm talking. If you guys do want any personalised tutoring, one-to-one style with a tutor like myself, then that is something that MyTutor offers and something you're able to access through MyTutor on our website. So do go and have a look if that's something that you would like. I'm just putting these questions up so that you can pause the video in the future and have a go at these questions. Okay, thank you all so much for coming. I hope you've learned lots. I'll see you guys next week for more physics GCSE webinars. Thank you.